Alright, in this video, we are going to practice several basic carbon chain naming components. So here are 5 molecules. Go ahead and pause this and see if you can name these, and then come on back and we'll work through them. Alright, well, let's start with this one on bottom. So I have a ring, and there are 1, 2, 3, 4, 5, 6 carbons. So this is right away going to be some kind of cyclohex. Cyclo for being a ring, hex for being 6. Now it has double bonds, so there is going to be an ene. Well, there are 2 double bonds. Well, in the same way, if we have 2 methyls or 2 ethyls, if I have 2 double bonds, I just call it a diene. So this is going to be a diene. I still have to specify where they're at, however, and for that we have to figure out the numbers. There's a bunch of different ways we could try to number it, but because it's a ring, we get to pick where carbon 1 is. So let's just arbitrarily pick this. That gives my first double bond, starts it at 1. We want it to be as low as possible. Now I have 2 options. I can go left and go 2, 3, or I can go to the right and go 2, 3, 4. One of those routes gives my second double bond at the 3, and one gives them at the 4. Many students will originally think, oh, I should go left. The problem is, remember that you have to pass through both carbons of your double bond. By picking that to be carbon 1, I must go to the right and make carbon 2 the other carbon of my double bond. And so the only option is 1, 2, 3, 4. And no matter which carbon you started of the double bonds, it's always going to be 1, 4. You can play with the numberings. You'll find that no matter what you do, you will end up with 1, 4 diene. So this is cyclohex 1, 4 diene. All right, let's go up and let's grab one of these other molecules. Let's look here at our 2 double bonds. So 1, 2, 3, 4, 5, 6 carbons. It's a hex again. So this is some form of hex. I have double bonds, and so it must be a hexene. And I have 2 of them. So again, it's going to be a diene. Now, if we try to number it, well, whichever side we start on, we're going to end up with, if I try the other way, 1, 2, 3, 4, 5, 6. Regardless of which direction that we number from, 2 and 4 are going to be our starting points. So it doesn't actually matter whether we start left or right, we get the same numbers. It's going to be 2, 4 diene. Now additionally, we didn't do it for the ring. We'll go back and explain why here in a sec. But I have double bonds. If I have double bonds, I have to consider whether they are cis or trans. And so if I put a line through my double bond, what I find is that one group comes in and the next one following the chain comes out the same side. This is a cis. Additionally, the exact same thing happens for my other double bond. If I go and put a line through and check it out, I see that my groups come in from above and they go out from above. This is also cis. So both of them are cis. That makes this a cis hex 2, 4 diene. So if you have multiple cis's or cis and trans mixtures, you just put them out front in the order of the number. So if you had 1 cis and 1 trans, if the 2 was a cis and the 4 was a trans, it would be cis-trans. In this case, they're both cis, so it's cis-cis hex 2,4-diene. Why don't we do that on the ring? It really can't be any other shape. There's not enough flexibility in a 6-membered ring to allow a trans double bond. In fact, you have to be up to 8 carbons before it is even possible to get 1 trans double bond in a ring, let alone 2. And so they're just not really mentioned in rings because they don't come up as anything other than cis. Let's jump over here to the right. This one is going to be a little bit more fun and complicated. So we need to think about numbering. Well, I could say, let's just start here on the end. 1, 2, 3, 4, 5, 6. And whether I went up, I would have had 5 and 6. If I'd went over, I would have had 4 and 5. So clearly the 4 and 5 route isn't as long as it could be. I'm going to have 6 carbons long. Doesn't matter whether I do the up or down over here on the right. It's still going to give me an ethyl at the 4 position. So either of these routes is acceptable to be the 5th and the 6th. Which leads me to another interesting conclusion is what if I'd gone 1, 2, 3, 4, 5, 6? Well, that also gives me 6. So which of these 2 routes do I want to follow? Do I want to follow the top one, or do I want to follow the inside one? If I follow the top one, I'll get an isopropyl group at position 3, and a cyclopropyl, we'll talk about that name in a sec, at position 3. However, if I follow the bottom route, I hit a methyl at position 2. You want the lowest first group that you run into. And so all else being equal here, taking that lower route will actually get me my lowest first group. And so I want to number it this direction. And so this is a hex. It's a hexane. There is a methyl here at the 2 position. There is a 3 position ethyl. There's a 4 position ethyl. And this is our most interesting one. At the 3 position, there's a cycloprop. And because it is a subgroup, it is a propyl. I mean, you can have propyl chains. There's no reason you can't have cyclopropyl chains. YL tells you it's a subgroup. We named for the big chain, there was a ring stuck hanging off the big chain. And so I can identify lots of little parts. I have 2 ethyls, and I have this cyclopropyl. Well, cyclo is not a multiplier, it's part of the name, so C actually wins. Way out front, 3 cyclopropyl. And then my ethyls. I have a 3 and a 4 position, which ethyl, and I have 2 of them, so it is diethyl. Need to move that hexane. And I have a 2 position methyl. I ordered my groups in the name alphabetically. So cyclo is not a numeric specifier, it's part of the name. So cyclo, C comes before E. Despite it being a diethyl, remember the di is a multiplier. It's telling us the number of ethyls. We don't alphabetize for those numeric specifiers. And then M, the methyl, comes after E. So 3 cyclopropyl, 3,4-diethyl, 2-methyl hexane. That is the name for this molecule. Well, let's look at this top one. A little shorter, a little more straightforward. 1, 2. If I'd started from above, it still would have left me a 1 carbon group on carbon 2. So there's a 2-methyl. Here's 3. Here's 4. Here's 5. Either way, I've got methyls, 1, 2, 3, 4, 5. So I have a 2,4 dimethyl pentane. And finally, our last molecule. Our last molecule, we have to find the longest chain. One, two, three, four. I could go 5 and 6, but I can clearly see that to the right is farther. So 5, 6, 7. If I tried to go along the top, I would have had 1, 2, 3, 4, 5, 6. Just because we tend to write them zigzag doesn't mean the zigzag is the longest chain. In this case, coming up from below or going down from below is going to give us the longest chain. In terms of numbering, 1, 2, 3, 4, or if we come up from the bottom, it still would have been 4. So it doesn't matter whether you start from right or bottom, it's going to be at the 4 position that we run into that ethyl. So it is a 4-ethyl. And so this is 7 long, so it is a heptane, and it has a 4-ethyl. Make it look nice. It is a 4-ethyl heptane. And so there was a little practice with larger subgroups, a variety of subgroups, a variety of position options depending on what chain you follow, as well as double bonds both in rings and in straight chain systems.